Well, hello, friends. Today it's the last day of my Christmas holiday, so I thought we would do something fun. And since we've been looking at so many exploits lately, a whole two of them, I figured we could try to make our own. And I was looking around the code a little bit, and I found a suspicious thing. But let me set the stage a little bit. So when we start a program in Serenity, say we start the ID program, right? Then what we're doing is we're telling the kernel, hey, load a program with this name. Specifically, it's bin ID that we end up loading. And then the kernel goes and opens that file and looks at the elf header, which is basically instructions for how to load it. And the important thing that we do is we iterate over these things called program headers. And the load type header here means that it's telling the kernel, hey, take this chunk out of the memory starting at this offset and with this size here, and load it at this virtual address in the process address space, right? And then it should be mapped readable, not writable, executable. This is basically the text segment that has all the code. And then here is another, also a load header, which says load from this offset into the file, this many bytes from the file at this virtual address. Although, even though it's only this large in the file, it should be this large in memory. So it will copy this many bytes from the file and then fill the rest with zeros until it's this large. And it should be mapped readable, writable, not executable. And then we have the thread local storage thing, but we can just skip over that right now. But I was browsing around a little bit and I realized that the kernel is basically just taking orders from these elf program headers, and it doesn't really think super much about what it's being told to do. And we can probably exploit that to build ourselves something like a kernel, like an arbitrary kernel memory read primitive. And let me show you what execution looks like. So this is for the exec syscall. And actually, let me take that off because it's pretty warm. So when we do exec, we check some sanity stuff, and then we try to open the file that you want to exec. Everything's fine so far. Is it executable? Otherwise, is it a zero length file? Can't do that. And then if all that looks good, then we map the file into a temporary memory area, and we create a new page directory, and then we try to load the elf into a new page directory and create like a new address space based on the elf contents. And that starts to happen here, where we instantiate an elf loader right here. And then the way that elf loader works is that it has these hooks. So elf loader is sort of independent. It lives outside of the kernel because it can also be used from user space. But it's just the same code. It's compiled in two different versions. But anyway, basically you give it an address to the memory where the elf is stored. And then we have these three hooks. There's the map section hook, the alloc section hook, and the TLS section hook. And these basically correspond to these three types of program headers here. Although they are both type load, we actually separate writable and non-writable, because if a section is not what a program header says, not writable, then we just will not map it directly from the file into memory, because since it's not writable, every instance of this program can share the same file-packed pages. Whereas with the writable, we have to allocate a unique memory region for this individual process and then copy over, or like zero it out so that it's this big, and then copy in this many bytes from the elf. And if we look at what map section does, for example, that's this one here, the non-writable, he just allocates a new memory region using an existing VM object. So this VM object we've opened up previously. It's basically just a VM object that refers to the executable that we're loading. So every map section just creates a new VM region around the executable at a specific offset with a specific size. And this one is not as interesting as the alloc section hook, because this guy, he will just allocate new memory, allocate this much memory basically, round it up so that it's a multiple of the page size, and then I'll show you what happens with that memory. We set it here, and then in elf loader, by the way, this is where elf loader iterates over all the program headers. So you can see here in the layout function, for each program header, we look at the header type, so TLS, skip over that one, but the rest are load, so these are both the load cases. So if it's writable, which it is for this one, then we take this path here using the alloc section hook, and for not writable, we use the map section hook for this guy. But if we look in the path that uses the alloc section hook, we can see that after it allocates this memory and it doesn't fail, it then copies the data from the elf executable at this offset right here, this many bytes, into this virtual address in the new process address space. And this mem copy here, it is very, very sketchy, right? Because it's just copying to, we know that this address here, we've allocated this memory just now. So we know that it's a valid address in the process address space. And we know that we are using the program header size and image. So we're using this size here to allocate it, and that has succeeded. So we know that it's like a valid address. But this right here, the program header raw data, this is just an offset into the program image. And this offset comes directly from the elf header. So I'm thinking we can use this to perform essentially like an arbitrary, we can read any memory that we want from kernel space and leak it to user space. And at least I think so. And I figured we would try to just build an exploit that does that, because that would be fun. So let's just call it something cool like hacks. It's pretty cool, right? And then how the heck are we going to do this? So I guess what we want to do is we want to create a new elf binary that that does something silly with the program headers, so it doesn't do the normal stuff. And we'll need some headers for that so that we know the structs and everything. Probably we'll want to be able to write some files and whatnot. Okay. So bear with me because I'm not used to this stuff. But we'll see how we can do this. Okay, so we just want to make one of these things. So let's just allocate some memory, first of all. Buffer, what do we call this? Buffer, yeah, whatever. Is malloc, say 16K? I don't know, that should be enough for anything that we want to do, right? And then I guess we want to open it up. We'll save it into something cool like X. It doesn't really matter. Maybe temp X. Create. And if that doesn't work, Okay, and then we'll write out the buffer. In fact, maybe we can just do this on the stack. I don't know why I thought that I needed this to be a heap allocation. Maybe 8K is enough also. Right, FD buffer, size off buffer. Okay. And then we can just close the FD. Okay. So first thing we want to do is we want to start poking an elf header into this buffer. I guess we'll zero it out first of all, actually. And then we will just take an elf32 elf header. Something like that. Oh, we don't have memset. Okay, and then I need a cheat sheet here. Just want to see what's what. Oh, that's not very impressive. But I guess we want to set the machine type. And I don't know, what does it even look at? We can look in an elf image to see what he cares about. Because when we load an elf image, we parse, and it looks at the machine type, has to be 3. And then it looks for string tables. I think we can just skip those if we don't have any sections. Because if we don't have, if I have 0 sections, it will just go directly and return true. And then elf loader, which uses this, it just instantiates it here, and then when we call layout here, it will just iterate over the program headers. So we just set up no sections and then set up like a program header to do what we want. So machine, that's the x86 baby. And what else do we care about? Yes, section header count 0, but everything's already zeroed out, so it doesn't really matter. Program header counter, we want to have, say, I guess what are we going to do? We're going to set up, first off, we need some code so that we can run a little code, and then we want to have one of these guys, but we want him to we want to set it up all sneaky-like so that it loads some kernel memory at the virtual address that we control. So we need 2 program headers, and program header size, I guess it's just whatever that is. I don't know if we even care about that. It seems like we don't. Well, since we don't care about it, then, or, well, let's see, what else do we want? Do we need anything else? ph off, I think that's the offset of program headers into the, right, so when the elf image parser looks up a program header, it looks at the raw data, which takes an offset, so it's just an offset into the file. So it's raw data with the offset is program header offset plus sort of the array index into an array of these guys. So this is how many bytes into the file that the program header starts. So we'll just put it right after the elf header. So I guess that's size of elf32 header, because then it comes right after. Okay, and then program headers is elf32 program header at buffer plus size of elf32 header. I guess we can even say header ph off. Okay, and then program header is 0. We want to set him up to be a PT load. And this is our code, I guess. So we'll set the, how do we set the executable stuff? Is that flags? Okay, let's look in elf image, how it's figuring that out. Oh, it's right here. Program header is flags, and then PFR, PFW, and PFX. So we can just say PFX, so read and execute. That will take the map section hook path for this program header. So then we'll say the p virtual address. If you could load me at, say, this address, pretty cool address. And offset in the file. I think that's, what if we just load it like, we start loading the base of the file. Doesn't have to be more complicated than that. And then the size to load from the file is, what if we just load the whole thing? It's pretty okay, right? And maybe we should get a binutil port to have inside Serenity, so that we can look at the binary that we're creating. Build faster. I mean, download faster. Am I forgetting something? We set the alignment to page alignment, because why not? P. I feel like that's everything that we need for that first program header. And then let's do a second one. But this one is going to be writable, but not executable. And we can load that at 3 fajillion. And of course, we should update the index here. So let's see. So this means that first we'll load some code. Well, we'll load the whole elf binary basically to this virtual address. 8 kilobytes starting at offset 0 in the elf, aligned to a page. That's cool. So everything will be here. And then for this part, we're going to load from the file, but what it's going to do is it's going to allocate. We have to. Oh, we're forgetting one thing actually. Forgetting to say how big it should be in memory. So in this case, we want the whole file in memory. And in this case, what if we want this to do? Say, I mean, I guess we can just load a whole page here. At this, oh, so this is, let's see. So we're going to trick it now into where the hell is this? Let me split this elf loader. So we want to trick this mem copy here, right? We want to trick him into loading from some kernel memory to this. So this will be hex 3 fajillion when we're here. So we'll copy from here to there, and this, we'll copy this many bytes, size in image, which is the file size, right? So we want to copy, say we want to copy 1 page, right? And that means that we have to change the p offset so that the base of the elf in memory plus the p offset is a kernel address. Now, this is going to be made a bit easier by the fact that Serenity actually loads elf binaries at the same frickin' address every time. So if you look at system monitor here, you can see that he's loaded at 100, 1000 hex. And everything is loaded the same because they just call the, everyone just calls the range allocator, and since it doesn't do any randomization whatsoever, this is just the first address that we give out. So we know that 100, 1000. So this is going to be the base of the elf in the process address space. So if we load from I guess the thing that we actually want, so say that we want like this address, then here we'll subtract the base, and this should give us a read from this address. I know that this one is never mapped, so let's just try reading that one and see if we can get a sec fault. I feel like I'm definitely forgetting a bunch of things. So I just want to see if we can provoke some kind of reaction. Hacks and exec format error. Oh shit. Okay. We failed where exactly? Failure loading X. All right, all right. Well, not to worry. I'm sure we can figure out why it's doing that. Failure loading. Since we control everything, we can just add some prints. So we're here, which means that either load returned not success, or the entry address is 0. So that's, I mean, the entry address is going to be 0. So we forgot to set an entry address. I guess we're going to need to have some code in this thing. So let's say code start. It's going to be here. So this will be after the program headers. Plus size of 2 program headers. So actually more like program headers 2, something like that. That will give us something we can work with, and then we'll do something like this. So code plus plus is, let's do a CLI instruction, just give ourselves a crash, because this is a privileged instruction, so we won't be able to do that. And then we just have to set up the header so that the entry is the code start minus the buffer, whatever we call it. Something like that. X. All right, so what did we get here? It's trying to read from this address. It's trying to jump to this address. Oof. What are we even doing? Oh, wait, hold on. It's trying to jump to that address because this is my entry address, I guess. I'm not setting up my entry very cleverly because it needs to be in virtual space. This was the virtual base of our code segment, so let's enter there instead. Okay. Failure to read an instruction, so we cannot jump to here, but this is I would like to see the memory layout after we load an executable. So let's see. So after the elf loader is finished, let's just say memory layout after elf load, dump regions. Okay, so this is the memory layout after the elf load. So we haven't actually succeeded in mapping anything. Just what is my phone buzzing about? Okay, it's not super important right now. So I guess we did not do the program headers correctly. What if we were to enable some debug output here? Just tell me what you're seeing. Okay, that's too much debug output. What the hell is that symbol? Okay, well, we don't care about symbols right now because our fake thing doesn't have symbols anyway. Okay, that's more like it. So hex, tmpx. Okay, so this is ours. It doesn't even print how many program headers there are. Should probably print those out. Program header offset and count. Wait, did I even make? Oh, I did. Okay. Okay, so we have two program headers at offset 52. But it seems like nothing happens with them. So what's up with that? What is this type none, by the way? Type, section type, file type to string. Oh, we could put that as our type. make a slightly nicer looking executable. E-type is that. Also, it's kind of annoying to type /temp every time, so we'll just call it X. But why doesn't it load the program headers? Let's see. For each program header, does this code even run? I feel like we should see sort of this thing right here. We don't see any PH anything. So what's up with that? So we can go here. Image is valid. Little layout. All right. Oh, I forgot to update the frickin' thing. Forgot to install the new Hex version. All right, Hex X, come on. Image is valid, will layout. Okay. For each program header, does what? Goes through the program header count and then calls a callback. So it's the header ph num. So it should happen twice. Are we not setting p to load? P type? Is this p type? Okay, well, why don't we just log something here then? Type. Type 0, type 0. Okay, so that's null. Okay, so maybe I didn't set up the offset correctly. What the hell did we say? The program header offset should be 52 bytes into it. And we put them at buffer plus that. Am I brain deading here somehow? What am I even trying to write here? I feel like I'm doing something brain dead. That assertion fails. Okay. So what am I trying to write here? Just the size of this thing. Okay, what the heck am I doing wrong? Why am I so blind? Why am I blind to this? I just want to go this many bytes into the buffer. Why is that so hard? Is that even what the ph off is about, by the way? It's ph off offset into the file ph off plus index times size of a p header. This is a program header. All right. So we'll do something like this, because now I don't know what I'm doing wrong, so bear with me. We'll figure it out. Program headers at 208. What? Is it because I am... I have to do something like this. Because I'm casting it to elf32p header and then stepping size of the p header instead? Yes, okay, that's it. All right, so more interesting. So look at that. It loads these two program headers, and then we even see that read from this address that we definitely should not be allowing. And that's in elf-loader layout. So I think we just subverted that memcopy there. So let's do something more sinister. Let's look in the kernel. We can just grab some symbol. Like that exploit the other day was doing G processes to find the process table. So let's get that one. This address right here. So what if we just put, oh, damn it. Come here. What, that doesn't work? Why are you this way? Okay. So if we do that, will it give us the contents of G processes? I feel like if we start this now, it's actually just going to run. Okay, so now it succeeded, and actually it got all the way to my faulty instruction there because I added clear interrupt flag, and it would gives you a general protection fault. And we can see now that the sections that we set up have been successfully loaded. So I think we should have copied 4 kilobytes basically from this address to this address. So let's see if we can read those out. I guess the easiest way to do that is to run this program and maybe make a pipe in between them. So something like this, and then we fork. Now we're in the child, and here we just want to exec the thing we just created. This should not fail. And then here we can just wait just wait for nothing. I mean, I guess we can, or no, but we need to just wait regardless. Okay, so now our problem becomes this process right here. It has this mapped into his memory, but we got to get it out of there. And we should put it into a pipe. And that process should now have a pipe open, but we need to get him to write something into that pipe. So we need some code to run on that process. And I guess we can just set up a syscall, really, because we have an address that we want to do a write into the his end of the pipe, and we just want to use 3 fajillion hex as the address to write from, and 1 page. So how do we make some code the easiest? I guess we can just continue this concept right here. I'll just make this with NASM. So a syscall would be, let me cheat. Write has 3 arguments, so it's this one right here. So move ex, whatever the write syscall number is. I guess we can figure that out. Ugh, it's deep into it. Can we figure it out somewhere? SC write is 24. All right. Thank you. Thank you, Q Creator. 24. EDX is argument 1, so that would be that virtual address that we want to copy from. And oh shit, no, we need a file descriptor first. That would be 0, 1, and 2 are the standard IO streams, and then 3 is the reader end of the pipe, and 4 is the writer end of the pipe. So then that's argument 2. And argument 3 is, I guess, 1 page. So something like that. And then, oh, we also want to exit, actually. So let's be nice and exit. Exit is 9. So first we make the syscall, and then okay, there's probably some easier way to do this. There's definitely some easier way to do this, but I guess this is how we're doing this. So B8, that's mov EAX, and which one's that? BA, B9, BB. And that's EBX, ECX, EDX. Then we need to do some store a 32-bit value here, so that would be SC syscall. Oh, let's get that. See, right? And of course, we gotta move forward this many bytes. And here we do, what was it? 4 for the, didn't we have the 550 set up? Oh no, it's later. Oh shit. Well, we know that it's going to be 4 anyway. And then here is our virtual address. then this would be our size. So how many bytes we want to copy. Okay, and then we just need to make the syscall. That's CD82. Okay, and then we want to also exit. So I'll just do, oops, syscall exit, and another int. Okay. Then if we get here, because the syscalls didn't work, then we'll still crash. I forgot to do something with with this. We have to do something with it. So after we wait on that process, we should be able to read now from the pipe. So we'll get a hex buff. And we'll read from the pipe at 0. Hex buff, size of hex buff. And print got this many sneaky bytes. And then we can maybe just read the first 4, because it should be G processes. So hex buff I. And yeah, whatever. So, oh, I forgot to say. Well, I don't know if that's the right value. We got to print it out somewhere so we can see it. Maybe what's the last thing that we see? Process destructor, right? So here, why don't we just print it out right here? Debug G processes is at G processes, bro. Okay. Poof. And G processes it at 40, 12, 28. So that's 40, 12, 28. It works. Pretty cool. So basically we were able to sneakily read kernel memory from a user space program by making sneaky elf headers. See, this is a lot more satisfying than just seeing the memcopy and then thinking like, you know, I bet you could exploit this to read kernel memory. Like to actually go through the process of doing it is pretty cool. Now, how do we prevent this? So let's see. I mean, the elf loader is going to need a lot of work to harden it because it's currently like not checking offsets or anything ever, anywhere ever. So it's going to need a lot of work to get that really robust. But I think we could probably do something. We can probably like neutralize this type of attack with some targeted fix at least. So the issue is, of course, that the offset is totally bogus. So we should verify that the thing that we are copying is from within the elf executable. Because if it tries to copy outside of it, then we shouldn't allow that. So, how do we do that? I guess if program header raw data, what is that even? Is that a const char star? Right, so raw data has to be, it cannot be before the image raw data. Can we even get the image raw data somehow? I feel like I would like to have an address. Okay, well, we can, maybe we can add something to the image. Let's say, is valid is within image. Const u8 star size t. Address. Okay, and then we'll check if address is less than m. Okay, where is it even stored? M buffer. Okay, so if it's less than M buffer, false. If address plus size is greater than M buffer plus M size, there is no M buffer plus M size. There's no M size. That's very silly. Wait. Why is that? Because we just set this up with a pointer. All right. Let's do a little bit better. So we'll require a size when we set up the elf image. Seems like a healthy start. Okay, and then who creates these? Elf loader. Elf loader constructor. Yeah, here. So we're gonna have to pass some size to elf loader as well. It's okay. Okay, and then who creates these? This guy right here. So we'll just pass along the region size. In fact, this is rounded to page size, so we know the exact size of the executable, so we should probably use that as the metadata.size. Okay. And then is this used anywhere else? Nobody makes these? Yeah, over here. Oh, but that's a dynamic object. Okay, so maybe that doesn't matter. Oh, it's on the stack here. Well, we can fix that. M file mapping. M file size? Is that the right thing? That's how we unmap it. File size is passed to us. Dynamic loader. Okay, that looks about right. Okay, so elf image should really be taking a size argument. Well, I agree, dude. What is storage even? This is module loading. Read entire file. Okay, that's fine. So, okay, what are we breaking now? Raw data. Oh, right. So instead of that thing I wanted to do, instead we'll ask the image, and image is within image the raw data with a size, program header, size, and image. So if this is not within, okay, what's wrong with this? This is const, this within. Well, this could just be a void star, it doesn't matter. Okay, so if it's not within, then we will say failed, true, return, also dbg, shenanigans, elf, writable, section, sneaks outside of executable. Okay. And look at that, shenanigans. And failed to load. Pretty cool. Okay, so that's pretty good. Man, we are gonna have to validate so much more elf things, I can tell, but at least this fixes this issue, hopefully, so that it's no longer possible to trick this memcopy to copying anything outside of the elf image. And I see there's some memcopy up here as well, so don't have to investigate it greatly, but we can still do the check here. If an image dot is within image, raw data, then we can do a shenanigans report here as well. TOS section. PTTLS header. Okay. That's pretty good. Let's just see that we didn't break anything with that, but I don't see why we would, because shouldn't be allowed to load things from outside the executables. Ah, it doesn't work anymore. Very nice. Okay, so let's see if we can tear this down into a patch. So g processes is out. Can remove that logging. This is just giving alpha image a size, adding some extra logging here. Maybe that is 0, we shouldn't, where was that? Here. Okay. Let's turn off the debugging. Is valid. Oops. Okay, so I think this is pretty good. I like this thing where we dump out the memory layout after an elf load, because we're just dumping out on the debugger, I think. Let's make sure that I'm right about that. Oh, no, I'm not right about that. Okay, I don't want these to be showing up in the message. If we can avoid it, because just trying to not show too many things in the message in general. Of course, oh shit, wait, that was before I recompiled. Dump regions. Or maybe user space addresses is okay, actually. The thing I don't want to leak out is kernel addresses. These are all user space regions, so it's probably okay. But we can put that behind a flag. So if def, do we have something for this elf debug? We'll just do something like that. Okay. Oh, we already have elf debug set here. Elf loader debug. I don't know if exec debug. Do we have something like that? No, we have fork debug. Okay. Now it's a pretty good patch. So just giving elf loader and elf image size, logging the program header offset and count. Then we added elf image is within image. Of course, we're also adding the size member to elf image so that we know how big it is. And these two shenanigan traps here in the elf loader. So if a program header tells us to copy something from outside of the image, then we will now refuse and fail the exec. So that's pretty good. Say kernel plus libelf. Refuse. Catch. Refuse to load elf. Validate pt load and pt pos. So that's before and copying. Before this, before this, it was possible to make the kernel copy from anywhere by setting up a pt load and elf executable with a program header instructing the kernel loader, specifying the loader, specifying that it, why is this so difficult? Specifying that you should specifying an file offsets, no? Outside the file. Since elf image didn't even know how large it was, it definitely we had no clue that we were copying things from outside our tidy up. Fix this by adding in size to elf image and validating program header ranges before them copying to them. The elf code is definitely going to need more validation and checking. Okay, so I think that's going to be it for today's video. But if you made it this far, then I thank you for watching and for hanging out. I had a pretty good Christmas holiday, I have to say. Very productive, and it's been very interesting, especially with the sudden shift to security-mindedness. It came out of nowhere there. So I guess thank you again to everyone who participated in sending me down this path, because I guess now we're doing this for a bit. But it's pretty fun. So I hope you saw something interesting here, and I hope I was not too slow or too newbie with the exploiting. It's not something that I'm used to, but it's something I need to learn about. So thanks everyone for watching, and of course, as always, if you're interested in supporting my work, you can always find me on Patreon, GitHub sponsors, and one-time contributions can be made via PayPal. But if you're not into that stuff, that's okay too. I'm just happy that we're all here and that we can maybe learn something together. So I'll just see you next time. Bye.